Okay, so now we are going to continue with this particular video on implementation of the code for solving a system of partial differential equation. Up until now we have looked at the shallow water equations, the kind of solution that we are expecting to obtain from it, and we have also looked at the Lex-Frederick-Riemann solver, and we have also looked how the eigenvalues play a role in the Lex-Frederick-Riemann solver. So these are the eigenvalues corresponding to the shallow water equations, and this is the flux that we are going to obtain in case of the shallow water equations. So this is the simplest type of flux that you can have, that is the Lex-Frederick-Riemann solver, using the Lex-Frederick-Riemann solver. So let's continue with the code now. Now in this code, the most important class that's going to change is this cell class, because now instead of having a variable for just a single array for the time steps, we are going to need a two-dimensional array which keeps track of the each time step, and per time step it should also save the variables, each of the variables of the conservative vector. Because if you look at the conservative vector here, now in this particular case it has got 3 terms which we need to store, and similarly f and g which are going to have 3 terms each. So we need to now keep track of more variables. So to start with, let me change this u to a capital U, and as you will see, the whole code will start showing so many errors. It's fine, we'll fix all of them. Secondly, we will need a two-dimensional array now, not a one-dimensional array, and we should put something in here to specify the size of the array. So what is the size of that array going to be? So to keep track of the size of this particular array, we will define a public, static and final variable. Let me put final up front. Public, final, static variable, and this variable I'll call it number of variables. Variables, and in our case it's going to be equal to 3. So this is public, static, and obviously it has to be an integer. So we have a public, static, final, int, number of variables, and that's what is going to go in here. Now that's not good enough. We also need the reconstructed values to be an array, and since these are since they were double earlier, it did not matter. Now we have to say, we have to initialize them. So this is going to be equal to new array of doubles. Oops, what am I doing? This bracket shouldn't be here. It's not an array of public, it's an array of doubles. So this is going to be double array of size number of variables, and this is going to be, I think I'll just copy paste this. It's going to be much more easier. So I'll have 4 of those, and I can just replace these names here. Oops. Copy paste, copy paste, and we are done. So now we have 4 variables, each of them being an array of doubles. Cx, cy is not going to change, dx, dy is not going to change because they are related to cell and not the variables. Total flux is now going to be an array of doubles, and the size of it is going to be equal to number of variables. So we have this particular thing fixed. Now the things that are going to change in this code are pretty simple. Everywhere, wherever we have u west, u west, u south and total flux, we need to put an additional for loop to loop through all the variables and just initialize it or repeat the operation for each of the array element. So that's it. So let's start with the initialization. So here, instead of having a single variable, now we have a array of variables or a vector of variables. So let me rename this to capital U first of all, and x and y gets fixed. Okay, so how am I going to initialize the shallow water equation? So let me use a Gaussian. So I'll say for I is equal to 0, let me just rename this to variable just to make it more clear. And the number of variables, does it not find out? Oh, it does. Okay, so number of variables, and this is going to go inside this for loop, and the second element of this, if you observe it, the second index is for the number of variables, and this will be important especially if you are coding in programming languages like C or C++. This using it as the second index will help in a better cache management. I don't think it matters that much in Java, but well, let me continue with that particular way of coding. So the second index is variable, and this value here is going to be a Gaussian, not a sine wave. So let me find out what that particular thing is going to be. So what are the limits? So in config file, we know that the minimum x is -1, max x is +1, minimum y is -1, max x is +1. So how does a Gaussian look like? So the Gaussian function is defined by ae raised to -x minus b square divided by 2c square. Now this is a one-dimensional function, so we have x. In case of a two-dimensional function, it's going to be the radius from the center. And the good thing in our case is that since we are going from -1 to +1, let us center the Gaussian at the center. Since we are going from -1 to +1, if our 0 is going to lie exactly at the center of the domain, so that is 0, 0 is going to lie at the center of the domain, so we can get rid of this b altogether because this is the shift from the center of Gaussian. I believe c is the standard deviation. So let's say the standard deviation is 0.25 or something, or say let us start with something like 0.1. Let us say c is 0.1 or say 0.2 or something like that. That is how much spread we are going to have in our Gaussian. And a is the amplitude, so let us have an amplitude of 1. So let's code this up. So amplitude, and let me make it a variable here. So double Gaussian amplitude is equal to 1. So we'll have Gaussian amplitude multiplied by e raised to, I think we have a direct function for that, EPS, okay, exp, it is raised to this, so we can use this exp. What goes in here is minus, and then so we'll have r squared. So r square is going to depend on x and y. So for a cell, x and y is fixed, so therefore r is also fixed. So we'll have double r, which is equal to square root of x square plus y square. So I think we have square here, so we need not take a square root. We can directly put r square here, and we can say it's going to be x square plus y square, so that will give me r squared. I can put r squared here, and what else? So minus r squared divided by 2c squared. So let me define sigma here, or let me say standard deviation, which let me say 0.2. So this is going to be divided by 2 divided by standard deviation squared, right? So let me call it variance, because variance is basically standard deviation squared. So I'll say 0.2 multiplied by 0.2. So our standard deviation is 0.2. So let me put variance here. So we have a function to start with. Normally what I like to do is, as soon as I do the initialization, I like to plot and see that the things that I have done is correct. So to do so, oh, there is a mistake here. Wait, not all the variables are going to be initialized like this. Only variable 0 is going to be initialized like this, because that's the height. The other two variables are going to be 0. So I think instead of doing this, a better way is to do something like this. So cell okay, so what can I do? Oh, so I can do something like this. So double say init values is equal to, and I'll make it an array of size number of variables. Copy, and the first one is going to be this, the second one is going to be 0, that is u into eta or u into h, and the third one is going to be 0, that is u and v are zeros. So now you need to initialize. If you look at the shell order equation, we need to initialize all these three variables, eta u and eta v. This one is equal to the Gaussian, this one is 0, and this one is 0 as well. So we have this initialized values. Now instead of saying it's equal to Gaussian, let me say it's equal to init values variable. Okay, so it's saying I can use some system array copy. Let me use that. So it does the same thing, it takes all the values, but depending on the implementation it may be a little bit faster, doesn't matter. This is much more clear, I believe. So values from init values are getting copied into this particular array. Okay, so initialization is done, but now next what I would like to do is I would like to plot it. So let me go to the main solver, and here let me call the initialization function. So let me see, what am I doing here? So I'm creating the cells of that particular size, that's all fine. So as soon as I create these cells in this cell class, these things will get initialized, and by default Java arrays get initialized with 0, so that's all fine. Then dx and dy is calculated, I don't have to change anything in there. This particular loop is going through all the cells, that's all fine. Dx dy is going to get initialized, it's all fine. Initialization is going to initialize all this. Yeah, I think I'm ready to plot now. So write solution. So now what I'm going to do is I'm going to go to this particular point in here, and well, I'm going to comment it out. I'm going to comment out everything below this line. So I don't mind if there are errors here, because they are never going to get called. I hope so. I think write function, writeable solution writer, yeah, that's the one that I need to change now. Now solution writer is going to write all the variables, not only one single variable, because now it's array that I need to write into the file. So this is going to be capital U, and this here is going to go into an array. So let me think about it a little bit. So for every row, for every cell I need to go through all the variables and the number of variables, and I need to put this line inside there. And I need to write that particular value. Now I don't have one value, but I have multiple values. So how many values are going to be there? Okay, now this is a little bit tricky, I guess. So I'll take this part, X and Y. Okay, let me just copy the first here as well. So in the so I'm going to write these two values, and I'm going to keep this value. I'm not going to put a new line there, and I'm going to put a space here, and I'm only going to write CX and CY over there. So this is done, and now after putting CX and CY, I need to only write those many values. So yep, I'll put a space here, and depending on the number of values, I'm going to write the first value. Then this is going to go away, and here I'll have variable. So once this line is written, so it's going to write X and Y. Then for each variable, it's going to write down the value, and after that I need to also write a new line. So I'll copy this and I'll paste it here, and I'll replace. In fact, I don't even have to do all this stuff here. What I need is only /n. Okay, so I think I'm done with this, right? So I am writing for each cell, I'm writing down X and Y location, then followed by all the values, then followed by a new line character, and we are, I suppose, done with the bare minimum thing. And here I can see some error. Why is it? Oh, the closing bracket problem. So I think I did this, so that should, I think, solve the problem. Okay, and now let me run this code and see what happens. So I'll run the code, and it will say that there are errors in the code. Let's run anyway. It runs the code and it puts something in the out file. So let me look at the code, out file, and it should write this particular file. Let me open it up and see whether I'm getting any useful thing. So I can see X and Y is being written. These values are very close to 0 at the beginning, and then they should go up to 1. Somewhere they should be 1, I suppose. So let me just search 1.00000. Oh, there is no such value. How did that happen? Or maybe 0.9999999. No, so there is some mistake somewhere. Or yeah, it's pretty much possible that it never gets exactly equal to 1, but it goes very close to 1 because of the discretization. Because only at one point will it be equal to exactly 1, but it will be very close to 1 at some place. So anyways, the best way is to plot it and check, but I'm a little bit lazy, so yeah. So I'm going to plot it and check now. So I have a code for plot 2D, so let me look at that particular code. Come on, start fast. I'm doing a live video here, come on. I don't have a lot of time. Okay, so I have this code here, and let me look at it's reading the solution file, and it creates a picture for all the files. It reads x, y, and u. So u is h here, so it should be fine. It will read the first three variables, and I think it will work without any problem. Let me just run this and check. Too many variables to unpack, so I think I'll have to h here. I'll have to put h u here and h v here. And here we'll have h. Here we'll have h. And here we'll have h. Okay, looks fine. Let me see what happens. Okay, so looks like the initialization part is fine. So we'll initialize our solution with this particular function. So let me just also put a contour plot here. Sorry, color bar here. That's what I meant. Is it UR or OR? I think it's OR. Okay. And I cannot see a color bar. Why is it so? Yeah, because it's the EOG which is showing the file, and since the save does not have it, it's not showing. Okay, so now we should see a color bar, and you can see it's going up to 1 and 0, almost 0 at the end. So this is the initial condition. So it's like the water being raised at the center of the domain to a particular height at time instance 0, and we will leave it at that particular time, with everywhere else the velocity being 0. In fact, everywhere in the domain the velocity being 0, only the height being changed at the center. Let us see how it evolves as the solution progresses. So that's our problem statement. We will use more complicated initial conditions later. Okay, now let's get rid of this and add some lines here. So we have written our solution. The start time is for calculating the time. Next equation, this is fine. dt. Oh, this is important. So now how is the time step going to get calculated? The time step will be calculated. Oh yeah, now earlier we knew that the advection velocity is constant, and therefore we could use a single velocity, but now we have to traverse through the complete domain and get the velocity. So what am I going to do is we know the maximum eigenvalue, which is what was that? So that was absolute value of u plus c and absolute value of v plus c. So come on. Okay, so we will define a private static and double get time step, or I'll say get time step for cell. So this is the function that I'm going to write. So given a cell, it should return the maximum possible time step for that particular cell. So what is the maximum possible time step? It's pretty straightforward. In fact, we can use these same variables right over here. So I mean, we can use this function. So it's going to be dt is equal to let me say dt1. In fact, I can use the same. These two expressions I can copy and paste it here. Okay, now dt1, I'll rename this as I'll rename this as DTX just to make the intent clear, and I'll make this DTY, and this is going to be CellDX, CellDY, and divided by absolute value of, I don't want to use the absolute value here, so what I can do is this has to be divided by math dot absolute value of u. Now what is u? U is now let me do this. Let me add a variable called u, which is equal to cell dot, I will also need, let me say, since I'm always going to look at RK step 0 while calculating the time step, let me just define step equal to 0, and let me also make it fine. Cell dot u, RK step is 0, and okay, and which variable am I looking at? I'm looking at the second variable, and divided by, let me also define double h is equal to cell u. Well, there is much more general way of doing this, and I'll be doing that later as we define the code, but as of now we are going to use we are going to calculate the time step only for shallow order equations, so that is why this particular code looks very specific to shallow order equations. So we have this. Now DTX is going to be equal to math abs of absolute value of u plus c. Now what is c? C is equal to square root of gh. Should I define g universally? As of now, let me not worry about it. Let me say I'll just type it wrong. G is equal to, or let me say gravity is equal to minus 9.81. I don't know whether it should be minus or plus, but we'll look at it based on the evolution that it produces. Okay, it's going to be math dot square root of, I wonder whether g has been taken as plus here, so x will have to, okay, I have to look it up whether this has been assumed to be 9.81 or minus 9.81. Are they mentioning it in the acceleration due to gravity? That's all they have written. And okay, I'll not worry about it as of now. I mean, I don't know what's the direction of the height, whether it's measured from down to up or up to down. So if it's measured from down to up, then g is going to be negative. Okay, so let me just continue with this. We'll look at it later. So gravity multiplied by h, so that's the value of c, if I'm not mistaken, square root of gh. So we have dtx defined now, and similarly we can write the other term which is absolute value of v plus c. Okay, now we have the bare minimum bones of time step that we need to now return this particular value. So we need to return dt, which is equal to 1 divided by dtx dy. So that's going to be the time step that we can have per time step, every time, the maximum time step that we can have in an explicit scheme. So then we'll multiply it by the current number, but now here we need to go through, let me put this right over here. Oh, actually I don't assume it. Okay, that's good. For I equal to 0, I is less than, this should now go through all the cells. So cells.length for j is equal to 0, go through all the cells. What I can do actually is, okay. Actually I should go only through the internal cells, right? So how can I get that thing done? So I can go to the number of x cells and number of y cells. So I have number of x cells, number of y cells. It should start from there and it should go up to the length minus the number of x cells and minus the number of y cells. Sorry. So I have calculated, I'm going through the full domain now, and now I need to say double, so minimum dt is equal to, let us say, let us start with infinity, why not? So first to infinity being the minimum step. Now if minimum dt is greater than the get time step for that particular cell, the cell I, j, if it's greater than this, then what am I doing wrong here? Get time step for cell. Okay. So if the minimum dt is this, then minimum dt is equal to, I don't want to call this again. So let me cut this and I'll put dt here. And I'll say double, let's not call it dt, let's call it cell dt. Cell dt is equal to that thing. If minimum dt is greater than the cell dt, then minimum dt is equal to cell dt, and we have the lesson. Finally, it should return minimum dt multiplied by the current number. Okay, now what I'm doing here is I start with some arbitrary large number, and then if minimum dt, and then I go through all the cells. All the internal cells inside, internal cells of the domain, and then I calculate the time step for that particular cell, that is the possible time step for that particular cell that is going to be calculated here based on the maximum wave speed that we have. Sorry. And then if the minimum dt, that is the current minimum dt, is greater than the cell dt, then we set it. Then minimum dt becomes that particular cell dt. So we will finally have the minimum possible dt. So I'll actually invert this. Invert it. Okay. So if cell dt is smaller than minimum dt, then I'll say minimum dt is equal to cell dt. That looks much better. So we have calculated the time step. We have also got rid of all the errors in this particular class, and it's time to test whether things are okay or not. So what am I going to do is I'm going to exit my code right over here. And I'm going to print out dt just to make sure that everything is fine. Let me just run this, run anyways, and it says infinity, which is wrong. So what mistake have I done? P is not going to be equal to 0, right? P will have square root of a negative number. That means gravity cannot be negative. Okay, that could be the problem. Anyways, and it still is infinity. Why is it infinity? Yep, it does not enter this loop. So why does it not enter this loop? So I is going from this should be number of ghost cells, right? What am I doing? What am I thinking? I don't know, somehow in my mind it was like here also it should be minus number of ghost cells. Somehow I was thinking that ghost cells is excess, I don't know why. So this has to be number of ghost cells. Yep, and now I believe it should run fine, and it gives me a number right over here, and I can calculate because everywhere u is 0 and v is 0, so all that it will depend on is this vx is constant. So c and h is going to be maximum at the peak, so at that particular point c is going to be equal to, let me calculate that, it's going to be equal to 1, which is the height, multiplied by 9.81, and the square root of that. How do I calculate square root? I calculate square root of 9.81, which is going to be equal to 3.13, and dx. So I have 160, so 2 divided by 160 cells, that is 2 divided by 160 is going to be 2 divided by 160, and then I divide it by this, so I should get this value, and I did not get that value. Yeah, that's because, okay, that's not the thing. So then I should px, these both are going to be same, so this value, so 1 divided by that value plus 1 divided by that value again, 1 divided by this whole thing, and still it's not working. What mistake have I done? And then current number is 0.5 multiplied by 0.5, and it does not match. That's I think okay, because maximum is not equal to 1. Okay, I can test it because I can see whether when it becomes smaller. So in this code what I can do is I can check, I can just print out the max value of h and let me print it out, and I think that should work. Yeah, so this is the max h that I need in my calculation. So let me do that. So this is going to be square root of that value multiplied by 9.81, and so that's going to be, in fact let me divide it straight away. So I'll have 2 divided by 160 divided by that value, so that should give me that value, and then I can multiply it by this divided by 2, so that should give me this, and then multiply it by 0.5, and that should exactly match with this number, and it I think does 9.982230. Okay, looks fine to me. So I believe it's fine. In fact, it's very important when you code to make sure that all your values are exactly the way you want them to be. Never take chances when it comes to code. Okay, I don't need this anymore. Okay, now we have gotten this done, so I can get rid of these two statements. Yeah, so I can get rid of this. If time plus dt is okay, this is fine. Now I need to go to the Basel operator. Okay, as of now, let us use periodic boundary conditions. I'll not worry about it much. So how can I do it very easily? So I can just add a for loop here for each of the variables. The number of variables for each of the variables. I should do that. Here this is going to be capital U, and I'm going to have variable here. It's going to be capital U, and I'm going to have a variable here. This is going to be capital U, and I'm going to have a variable here. This is going to be capital U, and I'm going to have a variable. Okay, so looks fine. So this is going to apply the periodic boundary condition for all the 3 variables. I obviously need to change it later on. As of now, I will go with it just to look that everything else is being tested fine or not. I'll just test everything else and then I'll look at the boundary conditions, because application of boundary conditions is a tricky thing and I want to look at it at the end. Okay, now this is going to be capital U, and I'll have variable here. This is going to be capital U, I'll have variable here. This is going to be W, and I'll have a variable here. Capital U, and I'll have variable here. Okay, so this is fixed. Next is variable reconstructor. Yeah, this is a very important step, and before doing this I am going to take a break because I'm really very hungry. I'll go eat something and come back. So I'll